So the example we're looking at here is we've been given the velocity time plot in the top, and we need to draw the acceleration versus time and the position versus time. Now you can see between 0 and 30 seconds, velocity increases at a constant rate because it's a straight line. Then between 30 and 50, velocity stays constant at 12 meters per second. And then at 50, it goes back to 0. So how would the acceleration versus time graph look like? Well, we know A is dv dt. So the slope of the velocity time graph, the slope will give us the value for acceleration. So between 0 and 30, we have a positive slope, and we can calculate that slope, and we see it's a positive slope of 0.4. So we know that between 0 and 30, the acceleration is constant, and it's constant value of 0.4. Then between 30 and 50, the slope on the velocity time curve is 0. Because it's a horizontal straight line, slope is 0. So that means the acceleration is 0 between 30 and 50. Now we need to plot the position versus time graph. Now we know that velocity v is equal to ds dt. So the slope on the ST diagram, that is ds dt, must equal the value for v. So we can go up. We can see between 0 and 30 that the velocity constantly increases. That means that the slope of the position time curve must constantly increase. So we have not a straight line, but a line that curves upwards. Then, between 30 and 50, we have a constant velocity. Therefore, our position, the slope on the position time curve must be constant and increasing because we have a positive velocity of 12. So, between 30 and 50, we have a positive increasing line with a slope of 12. Also note that by looking at this table, the position is the integral of velocity with respect to time. S is the integral of v dt. So you can get the value for the position by taking the area under the velocity time curve. So as we go from time equals 0 and move to the right, the area increases. And that is why the position also increases. Up until point t is 30. Then between t and 30 and t is 50, the area still increases under the velocity time curve, but now it increases linearly. So we only have a linear increase in position at the bottom. So these graphs relate to this table. And you can draw the graphs by looking at the relationships on this table. We know that A is dv dt. So we know that the acceleration is the slope on the velocity time curve. We know v is ds dt. So we know the velocity is the slope on the position time curve. And if you want to go from the bottom to the top, you can integrate. So we know that the value for position is the integral. That is the area under the velocity time curve. And also that velocity is the integral of acceleration. So it's the area under the acceleration time curve. So in an exam or a test, if you are given one of these plots and you need to create the others, just look at this table. Ask yourself, to go from this plot to the one that is asked, do I need to integrate? Therefore, do I need to take the area under the graph? Or do I need to differentiate? Therefore, do I need to take the slope of this graph to get the other value? I hope this makes sense. It's quite fundamental, but it makes a lot of sense once you understand it.